On the 21st of May 2002, Queen Elizabeth II was 3 days into a routine transatlantic crossing from England to America. On board, 1,457 passengers were enjoying the height of luxury, provided by 973 crew members. Everything appeared normal until the early hours of the morning, when a routine inspection in the aft engine room revealed every maritime engineer's worst nightmare: active, uncontrolled flooding. Seawater was pouring into the hull through an inlet pipe that was 250 millimeters or 9.8 inches in diameter. Making matters far worse, the rupture occurred on the ocean side of the main isolation valve, so the crew could not simply shut it off. They were facing an open hole directly to the Atlantic Ocean with 2,430 souls on board. I'm Chris Frame, and this is the story of how the QE2's engineers fought a desperate race against time to save the world's most famous ocean liner, using sheer ingenuity and an unlikely spare part. By 2002, QE2 was already a legendary ship. Launched in 1967, she was built to withstand the harshest conditions of the North Atlantic. For years, her massive machinery spaces operated seamlessly beneath the feet of passengers who were enjoying fine dining, lectures, and transatlantic leisure. On the 18th of May 2002, the QE2 departed Southampton. She was built for this passage, and the rhythmic hum of her diesel propulsion system provided the familiar backdrop to daily life on board. But to understand how a single pipe could threaten a ship of this scale, you have to look at how an ocean liner operates at sea. A vessel like the QE2 relies on vast quantities of seawater pulled in directly from the ocean. Seawater is drawn in to cool generators, support air conditioning, and feed evaporators, as well as for desalination, the process that turns seawater into fresh drinking water. These seawater intake pipes are effectively part of the ship's life support system. But they also represent a vulnerability. It is a controlled pathway allowing the ocean inside the ship, but it still lets the ocean in, so there's always some risk in these areas. In the early hours of the 21st of May, a senior watchkeeping engineer was carrying out routine rounds of QE2's lower decks. QE2 had two massive engine rooms, and as he entered the aft engine room, he spotted water accumulating fast on the deck plates. Following the flow of water, he traced it back to a primary seawater inlet pipe feeding one of the ship's evaporators. The pipe was 1.4 meters or 4.6 feet long, with an internal diameter of 250 millimeters or around 9.8 inches. Near the base, right where the pipe met the outer shell of the ship, water was flooding in under high pressure. This was a critical emergency. In standard piping configurations, if a component fails downstream, engineers close off the isolating valve to cut off the supply. But here, the perforation was located between the ship's outer hull and the isolating valve itself. So the valve was useless, and the incoming water was under direct hydrostatic pressure from the sea outside. The force of the incoming water was enormous, and left unchecked, the flooding would quickly submerge the lower engine decks, threaten electrical switchboards, and disable the ship's propulsion motors. So the engineering crew went straight into damage control. Their initial strategy was straightforward. They'd build a custom clamp lined with heavy rubber to wrap around the pipe and choke off the leak. While a team fabricated the patch, others activated the ship's bilge pumps to remove the rising water. However, the sheer volume of seawater rapidly overwhelmed the system. Within just 2 hours, the oily water holding tanks were completely full. As water continued to rise, 2 of the 9 main engines had to be shut down as a precaution. With propulsion compromised and water encroaching on vital machinery, the chief engineer faced a critical decision. To keep the ship afloat and operational, they had to bypass the holding tanks and activate the emergency bilge injection system, pumping the water directly back into the ocean. Under standard international regulations, discharging oily bilge water into open ocean is strictly prohibited. However, the MARPOL Convention contains specific exemptions for extreme emergencies where the safety of the vessel and its crew is at risk. So over the next few hours, the pumps discharged an estimated 400 cubic meters, or around 105,000 gallons of water, directly into the Atlantic. Meanwhile, the clamping attempt was failing. The pipe wall had been so severely damaged by internal corrosion that it was structurally fragile. Tightening the clamp further risked snapping the pipe entirely, which would tear the isolation valve clean off the hull flange and cause an instantaneous, uncontrollable flood. With the clamp failing and total engine room free-flooding imminent, the engineers had to innovate. A complete failure would exceed the ship's total pumping capacity, submerging the propulsion motors and leaving QE2 dead in the water in the middle of the Atlantic. But the crew devised an ingenious solution. If they couldn't seal the pipe from the outside, they would seal it from the inside. The engineers located a flexible inflatable rubber bladder, which was used as a spare component for one of QE2's hydraulic watertight door systems. They mounted the bladder onto a rigid sliding tube assembly and bolted the custom unit to the top flange of the isolating valve. Opening the valve slightly, they manually shoved the sliding tube down the throat of the pipe, positioning the inflatable bladder directly over the ruptured section below the valve. Once positioned, they connected a high-pressure compressed air line and inflated the bladder. The rubber expanded outwards against the inner walls of the pipe, completely blocking the breach and stopping the flood of cold water. This was a brilliant piece of maritime problem solving under extreme pressure, but the battle wasn't over. After several hours under continuous water pressure, the first bladder ruptured. Undeterred, the crew immediately pulled a larger heavy-duty replacement bladder, reinserted the assembly, and inflated it once more. The second bladder held. With the leak stabilized, the engineers constructed a custom steel box around the exterior of the damaged pipe assembly and welded it to the hull frame, creating a watertight cofferdam as a secondary defense. QE2 safely completed her passage to New York, where permanent repairs were carried out before she returned to service. Following the incident, the United Kingdom's Marine Accident Investigation Branch launched a formal investigation to determine how a safety-critical pipe could fail on a vessel with high maintenance standards. The findings revealed a complex combination of design and hidden corrosion. During QE2's major re-engining refit in the 1980s, her original steam turbines were replaced with modern diesel-electric engines. This specific seawater inlet pipe was manufactured and fitted during that overhaul. Because of its geometry, location, and the length of the inside of the pipe, it was almost impossible to inspect visually or clean during routine overhauls, and internal examination was severely limited. The investigation discovered that an internal root weld on the flange had gradually degraded over 15 years. Seawater had penetrated the tight crevice between the pipe wall and the flange structure, setting up the conditions for corrosion. Over time, the metal was eaten away from the inside out until it finally failed. Remarkably, the very pipe had undergone ultrasonic thickness testing just 2.5 years prior. However, standard ultrasonic testing methods could not detect the localized corrosion hidden beneath that specific flange joint. The official report praised the resourcefulness, speed, and technical proficiency of QE2's engineering officers. Their improvised bladder device turned what could be a major maritime disaster into a temporary delay. As a direct result of this event, safety recommendations were issued to Cunard Line, the QE2's operator, and classification societies worldwide updated non-destructive testing protocols for safety-critical water piping across the global commercial fleet of ships. It serves as a reminder of the skill of modern marine engineers who work out of sight beneath the waterline to keep ships safe. If you enjoy deep dive maritime investigations and ocean liner history, you can support this channel by checking out my book, The Evolution of the Passenger Ship, or joining as a member. It'd be great to have you on board. And if this story hasn't put you off taking a cruise, don't forget to check out my referral link to book your next holiday with Travel Masters, the very same travel agency that I use. Thank you for watching. Don't forget to like, subscribe, and let me know your thoughts in the comments below. And until next time, I hope to see you on board.